Before we get started, can you tell me a bit more about yourself? And I understand that you taught yourself machine learning. So what sparked your interest initially?
Well, it's funny. The expression "teaching myself machine learning" sounds like one day I just decided to embark on learning all of machine learning. It was a little more complicated than that. I sense like I've just always been interested in questions, and I've always been, well, this is a very interesting problem. Like, how can we solve this, or what are the nuances of this? So a lot of my career trajectory has been odd, I would describe it as, but mainly because I've just become progressively more and more interested in problems that the best solution appears to be some of the machine learning approaches. So maybe I'll provide some context that might be helpful. I grew up mainly in Mozambique. My parents met in Sudan, and they are currently in Liberia, but I've lived in Kenya, Lesotho, Mozambique, Swaziland, South Africa. So we were moving a lot, but when I came to the US for my undergraduate degree, I came and I was very much adamant that I wanted to be an economist, mainly because the people that I had seen that were very technical in Mozambique were these economists from the World Bank and working with the IMF, which is kind of like an odd perception to have. But I was very interested in learning economics and then working at an institution like the World Bank. And when I graduated, that's actually what I was first working on. I did economic modeling and statistics, and I was working with a group of PhD economists in Oakland and Berkeley. And at the same time, I started working on problems with nonprofits that were all over the world, and this was in my free time. But what was the turning point was that I was working on these problems with engineers and with researchers in the Bay Area. And it was almost as if like this whole other world had been opened up, where there were these tools that were very powerful for mapping large volumes of data. So one of the problems that I worked on immediately before BRAIN was this problem of like detecting illegal deforestation. There was audio stream from all these recycled cell phones in different rainforests. So huge volume of data, very different environments in different domains, so dealing with test set adaptation. And the goal was, hey, we have this streaming audio. Can we determine when there's illegal deforestation happening? And can we send an alert to conservationists? So that was kind of perhaps when it became like, this is what I want to work on, because I just found it so fascinating. And there's like so many sub-layers to that problem. And then when I arrived at BRAIN, like mainly the question I was trying to figure out is, do I like research? So yeah, that's perhaps describes my self-taught trajectory, which is not very, I guess there was no grand vision of it. There was more like just these sub-modular steps that I was very interested in.
Awesome. And so I know you founded a nonprofit called Delta Analytics. Is this what you were just mentioning before?
Yeah. I founded Delta 4 years ago. And Delta, some background is that Delta is entirely volunteer run, and it's far bigger than just me. It's made up of engineers, researchers, data scientists in the Bay Area, and the goal is twofold. One is that connect with other nonprofits and provide data consulting and data modeling for them for free. But then the second is how can we think more fundamentally about bridging the technical skill gap? And that was actually like one of the starting reasons I really thought Delta was quite exciting, was that essentially right now you have a handful of cities in the world where there's technical and research capacity to tackle some of these questions, and those you can list them on one hand. But the problems, and the most important problems, are not necessarily co-located with that concentration. And so really, it almost feels that, firstly, building up capacity through these educational programs is very exciting because it's also very informative for the people involved. And ultimately, it's much better than the 6-month programs that we will continue to engage in, but ultimately have to come to an end, where we have to say to the nonprofit, oh, well, our volunteers are done now. And the nonprofit, it's often this very uncomfortable transition where they're like, oh, but we still don't really know what to do. So that was what that was trying to get at.
Awesome. Can you tell us a bit more about your role at Google Brain? And can you answer the question you just posed before, which was, do you like research?
Oh, yes, I left a cliffhanger for the... do I? I really do. I really do like research, but I also like applied. And I think that's like... it was useful for me to have done both, to understand the pros and cons of both. Research is very exciting because you get to follow to completion, like a question that you're thinking about. And it's very exciting because in some ways, a lot of it is about how do we measure progress on sometimes problems that don't have clear metrics to say this is a success and this is not. And maybe I'll make that concrete, but like the problem that I worked on at Brainfield last year is interpretability. And it was really understanding, are we actually making progress in proposing reliable methods that explain model predictions, and which is a difficult task because essentially there's no ground truth. If we knew what was important, we wouldn't have to be interpreting it in the first place. So that type of framework and that type of discourse was very exciting to me. What I'm doing at Brain is, perhaps now that I've jumped ahead and said that, don't worry everyone, I do like research, is I'm part of the AI Residency program. And that program is really built out so to bring in researchers from different disciplines, people who have done their PhDs, people who have done their masters, and people like myself who perhaps poorly could be described as self-taught but have not done research before. And then this year I'm going to the new Accra Ghana lab. Yeah, which is
so exciting.
It's so exciting. It's so Mustafa Cisse, he was previously at Facebook. He started the Accra lab, came over to Google this year. Perhaps this is a fun fact. I'm not sure if, I don't think he will mind sharing. But the whole idea of starting this research lab in Ghana started last year at NIPS, at the Black and AI party. Mustafa and Jeff Dean and staying together in a corner for like 2 hours just talking, and talking about the impact that doing research in Africa could have. Not because you're saying, oh, we're actually going to do this, this, and this. It's a research lab like any other. We're just doing research. But because like the externalities of the presence there lift the ecosystem as a whole. And like how do you couple that? And like you've leveraged that energy to build up capacity. So yeah, I would do that. We all moved to Accra in December. So, yeah.
It's exciting to see the residency program grow. It started with Mountain View, New York, Montreal, Toronto, and now adding Accra and Zurich is just a testament to our desire for diversity, I think.
It's incredible. I would even say it's very important because the concentration, so progress in this field is actually, if we look at deep learning, it's still very new in terms of clear breakthroughs. And so there's a reason most of my senior colleagues come from the University of Toronto or the University of Montreal. It's because these were the universities that continuously funded AI. And that kind of gives you this really interesting snapshot into two things. One, that there's still a gap in experienced practitioners who can pass on skills, and there's almost this, there's very few places you can go to be at the cutting edge of research still. And I hope that I think the efforts of the residency are a key part of changing that. Because you do accelerate your learning when you work with people who have tried all the things that you want to try and say, no, 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 I did it, that didn't work. Or perhaps like it may work now, but it may work in a different way. So I think that's very, very useful. And like broadening that discourse as well is also fascinating because really, the other thing is that people who have been thinking about a different field often ask very basic questions that perhaps someone who's too deep in would say, oh, that's too basic. Yep. And they're often the best questions. Yep. Because, and perhaps I'm not talking directly about myself, but I often find this when I teach, is that the people with the best questions are people who have not done a lot of work in the field, because they don't have the baggage of feeling that they shouldn't ask it, and those are the ones that are very tricky to answer, because they get to the heart of, but wait, what is this? Yeah. Yes, why? Yeah.
So what recent advances in AI are helping you with the work that you're doing today in Brain?
So perhaps I'll do a little bit of a cheeky answer to this one. I think that a lot of my research problems have been created by the advances that we've made in deep neural networks. And I'll talk about the current subject of my research, who I'm working on with my collaborators, including Mustafa actually, and it's compressing deep neural networks. And why that's spurred by advances is that essentially, like, a lot of advances in deep neural networks, and I'm thinking I'll make it tangible by talking about computer vision, decrease in test error has been associated with deeper networks and more parameters. And so we've seen, if you think about the Linnet model, and now you think about inception, ResNet is slightly, I believe, better parameter-wise, but essentially you just have explosion, millions of parameters. That raises two questions. One is, a lot of these parameters appear to be redundant. So there's a fantastic paper, I'm trying to recall the name, but they show that a few weights can predict 95% of the feature maps in networks. So there are some interesting questions about why do we need so many parameters. We can also remove these parameters after training. We can remove 90+%, and on smaller networks appear to still retain an amount of accuracy. And these both indicate that it appears that we need a lot of parameters to achieve the test accuracy in the first place, but we don't quite understand why we can remove them and still do okay. And that's like an interesting theoretical problem, and also has implications for interpretability. The second reason, looping back to why this is fascinating, is that when we talk about democratizing AI, and when we talk about really having the research cross the boundary into providing impact in fields like healthcare and really allowing people to own AI, it really is edge devices. I mean, the communities that I grew up, it's spotty internet, you are very aware of data usage, and you are very conscious of how your phone is often one of the key ways that you interact with the world. Like, essentially, you've skipped laptops in many cases. Right. And that's very interesting as a problem, because when you have those severe constraints, it often drives novel ways of thinking about the research itself. Mm-hmm. There's a fun example, perhaps I'll share, but tell me if I'm talking, I'm also, please guide my dialogue in case I go too far. But this is really fun. So when I was teaching in Kenya before Brain, we were using a local data set of Kiva loans, but we were also working with a local nonprofit called Ineza. Ineza does pre-smartphone texting technology. And so the reason I mention NESA is not because we can deploy neural networks to pre-smartphones. That would be quite, that would be a headliner. But no, the reason I mention them is that we saw these very interesting patterns in the data. They are targeting students in secondary school. And the students are using the quiz bank, texting in, to study for their national exams, those big national exams. But what we would see is that all these students were using this pre-smartphone texting bank at like odd times of the day. At like 8 p.m. to 10 p.m., you would just see spikes in usage. And it was really odd. I'm curious, why do you think that was the case?
Spotty availability of the service?
No. Well, that's the cool thing about this is that it was text-based. So it was getting to a lot more students because you didn't need like internet connectivity. But yeah, what do you think? Yeah.
I don't know. Do you guys have a guess?
Can you define odd times of the day again?
So evening. So it was like when you would not expect primary and secondary students to be using a phone.
Well, they were supposed to be asleep, but they were texting their friends.
Well, no, because it was quiz bank usage. So all you have is like what they were doing on the quiz bank. So they were using it to study. Yeah, this is all in preparation for the exams. So I will,
International tutors?
Oh, no. So the fun thing about this is that everything is in a quiz bank, which the team on the ground prepared. But the answer to this reveals a lot because there's often a single cell phone per household. And so I love it. Everyone's like, but it's fun because it captures a few things. It says that like this is a shared cell phone for a household. And it also it shows like how the way that we think about cell phones might be different. That the families are like sharing this around so different people can use it. Because of this, NESA also realized the parents were using the quiz bank, so they started creating like quizzes for adults, which is really funny, but very useful. So these type of things. Kind of bringing it back to our conversation, but this is the characteristics that describe a lot of where most of the world lives. And so it's very interesting to think about if we really want to make things, AI first, if you think about the hashtag, but more fundamentally, if we want to just like advance research and see many different people owning AI and contributing to AI, then it's a really cool problem to think about. Yeah, that was perhaps a long answer. I hope it was somewhat useful, but
it was.
Okay.
Absolutely. And so can you give us some examples of industry applications of your research? And do you have concrete things that you can share with us, how we could use the research you're doing?
So my research over the last year, unfortunately, was fairly grumpy research. So the problem I was looking at was really an interpretability method, and I was looking specifically at explainability methods. So explainability methods for deep neural networks are methods that say, for this prediction, this is why the model, for this input image or input example, whatever the domain is, this is why the model made this prediction. So there are many, many possible methodologies for estimating what was important. And what I was asking was, a lot of the body of literature is trying to prove the contribution or measure progress on the task by asking, is this meaningful for a human? So is this considered more trustworthy for a human? So they might do a human study and say, relative to these other prior methods, is this method, do you trust it more? And I was asking a separate question where I was saying, okay, that is very, very important, but we must also guarantee that it's an accurate reflection of the model. And by that I mean that you can have a explanation that humans really like, because it might be perhaps match or align with our own values and intuition. But my suggestion was that does not guarantee that it's actually what's happening. And so to address that, like I worked on really with my colleagues, like protocols for assessing reliability, and how do we define when there's points of failure. So that's perhaps why it's a little grumpy, but I think it's necessary, because once you identify points of failure, firstly, it has really big implications for how the research directions change, because research is this very prickly, iterative process, and so it's often only when we fail that we know not to get too far in a certain direction. But also research tends to be sticky in other ways. So for example, there's been many of these methods that are all trying to identify a subset of pixels, and perhaps what I was interested in saying is, well, we have about 20 plus methods now all doing these estimates. We need to have some way of evaluating whether we're actually making progress. Yeah. The tricky thing about my work is that it requires, it's perhaps the first step, but it's essentially interpretability is, there is no finish line. And so in fact, like what I think was most interesting about it is that you understand that after working on this problem, it has to be an iterative process involving many different nuanced, formal ways of measuring failures, but also we should qualify different desirable properties, because meaningful, reliable, there's also other properties that people are interested in, like completeness. You want the attribution to sum to one. I'll stop there. I've thought about this topic probably too deeply. I'll go down a tunnel for too long, but let me.
I think your work is so important. Interpretability is such a key point to fairness, and so it's so awesome that you're working on this and thinking about this and keeping this top of mind.
So I will say one perhaps caveat there is that interpretability is a means to think about fairness, but they're not quite the same, mainly because you can arrive at what you think is a fair model without any interpretability. Yeah. So that they tend to be grouped a lot, I think especially recently. Yeah. But the fairness, for example, is very, a lot of it depends upon understanding what you want your definition, your initial definition, which implies your end goals. Yeah. Whereas interpretability, it can be as fluid as you are trying to investigate something using a visualization tool. And you may not have any end goal. And so while I think that interpretability is a key tool to try and understand whether we've arrived at fairness, it's a little tricky to group them together. Sorry, grumpy researcher caveat there, but go on.
Okay, so you mentioned a bit earlier that you were teaching in Kenya, and I know that the machine learning class that you were teaching is now being taught in Morocco. How important do you think diversity and accessibility are to AI?
Oh, very. Very, and I will say, I want to anchor this a little. So I think it's important because we tend, as humans, we tend to weight what's immediately in front of us quite heavily. We might be a little reluctant to admit that, but for example, the reason why I went into a very nuanced fairness interpretability is because I'm thinking about that a lot. But to someone who's in this room or viewing, they might be like, oh, she just went on quite a long tangent about this perhaps like arcane distinction. So we're a product of our vantage point, and we're a product of like our immediate experiences more than we would like to admit. So it's when I think about diversity, there's many different layers to that, but I broadly think about it in terms of if we were to chat, we would likely have some shared experiences because we are women. I also, when I was recently in South Africa at the Deep Learning in Daba, I had many shared experiences with those students because I remembered how little, for example, when I first came to the US, there were some things that were very just culturally alien to me. Like people would ask, how are you? But they wouldn't expect an answer. That was so confusing to me. And I would always be like, oh, I'm fine, I'm doing this. And then they would just feel, they looked just scared for their lives. So I think there's just some reference points that you have from perhaps where you grew up. But there's also things which is your ability to question. We mentioned this earlier. I mean, the only other thing I'll say there is that research is quite a prickly discourse because it requires, there's a very narrow set of mediums and language to talk about things, mainly because at the point when you're doing research, you're trying to push the field as a whole forward. And so you have an assumed body of knowledge with other people. That can come in the form of poster sessions. It can also come in the form of what benchmarks you use, what problems you think are interesting. Benchmarks are the way that we show that we're better than the author before, the way that we show that we tell ourselves that we've fallen short. However, there's inertia to benchmarks, and often it takes new people coming in to say, this is not the right way to measure progress, or maybe we've overfitted. Because I'll perhaps talk about like an ongoing conversation now in the field, even about adversarial examples. Adversarial examples there's been this very tight framework of talking about them. These are almost, the way people have structured these attacks is as almost imperceptible changes to the human vision that can still alter the prediction. However, research, I'm thinking of two researchers in particular at Brain, are saying, well, is that a useful framework? Because we're not doing very well at it. So it's not clear, like, are we learning useful ways to improve from it? But also, it's not how attacks would be done in the real world. In fact, we can show that there's ways to evidence how brittle models are that don't require imperceptible changes. So these type of, the ability to be frank and to question and not to have a body of citations behind you that makes you anchored to a position is exciting. And that comes with bringing new people in, but it also comes with bringing in different perspectives.
So how do you think we encourage people of all genders and backgrounds to come into the AI conversation?
I don't think people need encouragement. I think people need access. I really do. I will say this. So I'll mention the Deep Learning Endowment, which brings students from all over Africa to Cape Town. It is just you can just see it. Like, people are just so excited. Like the energy is something that's hard to describe, because it actually, like, oddly brought me back to when I first got really excited about deep learning, and then I was like, this is what I have to do, and I'm just gonna do this every day until someone just decides that they'll I don't even know what the verb I was expecting was, but like I was just like, it was to the point where I said, even if no one wants to work with me, I'm just going to work on this. And you can see it in the students. I think the problem is that firstly, all of them are learning online, which is incredible in some respects, but also that's why there's so much energy, because the ability for them to connect with even other students is such a rarity. And that's what's quite lonely, I think, about the journey of many people who are very excited about this topic, is that it is a lonely, self-guided journey. And in many communities, probably even here in Toronto, a lot of people are just studying online because there's a scarcity of people with the knowledge to guide. That's changing. I think that in very little time, educators have stepped into the market and are really sharing their knowledge. And also, I think the other advantage that deep learning has, and actually I'll broaden that and I'll say computer engineering and machine learning, is that there's a very, unlike other subfields of research, we don't restrict ourselves to publishing in Nature. There's actually like a very good culture of open source. where code, almost to the extent that you have to essentially retreat into a cave to not feel overwhelmed at times, because it's just a flood of constant contributions. But that I sense is what is the key advantage. In some ways there are walls, but in other ways there's so many different mediums to participate in. So even if you're not at NIPS, you can put good work on archive, and it's not as if you cannot. It's not as if you will be ignored. Yeah.
Publications to archive in the recent years have actually beat Moore's law. So that
oh,
really?
Yes. That's so funny. I guess that funny that wow. Well,
impressive, right?
Yeah. Well, perhaps that is also says something about our expectations for Moore's law, because unfortunately it's slowing. Unfortunately, people are not that optimistic that we will continue to see it hold. But it's incredible. It's frankly amazing.
It's a testament to, I think, how early people in the field will publish, and how open to comment and feedback they are, and how researchers build on each other's research. So it's such an active community.
It's amazing.
So what's next for you, Sara?
Accra, Ghana. I've been told there's a contentious culinary adventure awaiting, because Mustafa's from Senegal, and he is adamant that the jollof rice from Senegal is far better than the jollof rice for Accra. So I think one of the first events we'll have is a jollof off at the new office. But I think more broadly, I'm really excited about model compression right now. It feels like one of the most important questions to work on. I think I will likely return to interpretability, but I get excited to switch to some of these subfields are not as distinct as we think they are. I'll mention two examples. One is that adversarial, there's interesting links between adversarial examples and interpretability, mainly because we structured the whole adversarial space as human perceptibility. And that's very related to what we actually think about when we think about interpretability. A lot of times when people say this is more trustworthy, it's because there's higher perceptual quality to the explanation. So there's very interesting nuances. By the way, that was a conjecture. But I sense that a lot of our human trust is how much it aligns. And part of that for computer vision models is whether it's perceptible. So these subfields tend to both overlap in interesting ways as well as inform each other in interesting ways. I would suggest the same is true of model compression and our understanding of really the disconnect between using test set accuracy as a means to measure generalization and some of the very important work in recent years showing that high test set accuracy models still have the ability to memorize. And so I think that, and I'm thinking specifically of a fantastic paper which essentially shuffles the labels. So the labels are garbage, but still trains a model on this shuffled label image data set and attains a high test set accuracy because the model has enough capacity to simply learn what all the images are. So even though it's a cat perhaps and the label is like man doing woodworking, I think there are such labels. I actually, at least I've seen like a woodworking table something variation. Anyways, so even with that garbage label, it's still able to associate man woodworking with this cat image. And why I say that has interesting connections to model compression, well really, one of the fundamental reasons why it's interesting that we can arrive at more compact models is that it's an information theoretic perspective, which is that we really want to find the most compact representation that's still effective. And clearly the overparameterization, clearly these discoveries are suggesting that test set accuracy is not really capturing the entire story? And can we do that in different ways? So perhaps those were some rounding thoughts on like on what I find interesting. Yeah.
So how can we keep up with you and see how your journey in Ghana goes?
That's so funny. Someone just asked me for a business card outside, and I was like, I have no business cards. I'm happy to chat. I'm happy to provide my Google email. I'm on Twitter, so yeah.
Wonderful.
Yeah, happy. I think this is another misconception about researchers at Brain, is that we actually get a deceptively small amount of email because we're never in meetings and we're doing research. So you'd be amazed how pleased we are when someone emails us. So please reach out.
Do we have any questions in the audience for Sara?
So you mentioned that making models smaller helps in interpretability. You explained that removing extra memorization or redundant weights may help with making smaller, but how does it help in interpretability?
Yeah.
Would you mind repeating the question?
I will. Okay, excellent. I love how you prompted. Yeah. Your question is very good. Like what you're asking is, I mentioned two things. I mentioned firstly how we can understand the connections between model compression and wider commentary on generalization. But I also did a throwaway comment earlier, which was, oh, it could have implications for interpretability, and I didn't really dig into that. So it's a little tricky. I guess, so I'll mention why I say that is that there's actually, there's two separate works which arrive at slightly different results. And I actually find both of them quite interesting, so I'm kind of processing an opinion. But let me start here. So Chris Olah was at Google, now he's at OpenAI. He did fantastic work on interpreting, like visualization of neurons. I say fantastic work, but I will hedge it in a grumpy way. He really looks at essentially what is the role of a neuron. And he has various examples that show that this is perhaps a dog neuron. I'm simplifying the discourse, but essentially he ventures that neurons are associated with certain features and respond strongly to it. There was another recent paper by Marcos and DeepMind, just saying, we haven't gone to the model compression part, but I'm giving you the backstory, which is relevant. So Marcos and his collaborators at DeepMind also did a paper, and they suggested something slightly different. They suggest that if there is a kitty neuron, it's probably related to the generalization ability of the network. Meaning, he did this study where he removes neurons from the network progressively, and he shows that, and I say he, please, wherever I say he, insert co-authors. He finds that really good networks that generalize well seem to have more diffuse meaning. They don't seem to be attached to any one class. And the third paper, which will bring us to our, I guess, upswing and where I am with this, is that Bole Zhu and his collaborators recently did a paper addressing the second. And they were saying, well, we find a little bit of both. They say, well, when you remove one, when you look at class level accuracy rather than overall accuracy, it seems to be important for some classes, certain parts of the network. But then at the end, they say something which is deceptively in the last few paragraphs. I remove deceptively, say interesting in the last few paragraphs. But they say this, they say, but if you add batch norm, and I believe they also think about dropout, you no longer see the same concentration of like a feature in a certain class. So how does this all relate to model compression? Well, in all of these papers, they were removing parts of the network to try and understand what was important for what feature. And I think there's some very interesting directions there. Both understanding whether we can actually say this is a kitty neuron, But also, more fundamentally, when we remove all these neurons, how does it change how strongly the neuron responds to a certain class? And to wrap it all up in a bow, like, how does that also relate to generalization? So there's a lot there. I think the intersection of the fields is very new and not clear yet. But it is a promising direction, because at least what it does is it moves interpretability from always assuming that we start from a trained model. And actually, when most methods now, you start with a trained model, but there's actually very few degrees of freedom at that point, I would venture, because you've already optimized using just optimizing for reducing your loss. There's no constraint there that it should be interpretable. So at least with thinking about model pruning, you're actively trying to arrive at an architecture, and you might not necessarily be doing it at the end of training. You might iteratively be doing it. Yeah.
Thank you so much, Sara. We wish you good luck.
Oh, excellent. Yeah, lovely to chat. Yeah, yeah.
To chat with you.
Thank you. Oh, wonderful.